One scientist created 3 inventions. They were not weapons. They were not built to kill. They were engineering solutions. Together, they are believed to have contributed to the deaths of millions of people. They lowered average human intelligence across entire population. They altered behavior at a societal scale, and they triggered 2 environmental crises that are still unfolding. At the time, none of this was visible. The inventions worked. They solved real problems. They were praised as progress. Cars ran more smoothly. Homes became safer. Modern life accelerated. The damage did not arrive as a single event. It accumulated slowly, measured in exposure, measured in years. By the time the consequences could be traced, the causes had already become part of everyday life. This is not a story about intention. It is a story about outcome. In 1944, a young chemist named Claire Patterson went to work on the Manhattan Project. His assignment was precise. Separate uranium-235 from uranium-238, 2 isotopes. Nearly identical, different only in mass. The work required machines built for extreme accuracy. Mass spectrometers capable of detecting differences smaller than a fraction of an atom. After the war, Patterson returned to graduate school. He chose a different question. Not how to build weapons, but how old the Earth really was. The method relied on radioactive decay. Uranium slowly transforms into lead at a fixed rate. Measure the ratio. Calculate the time. To calibrate his instruments, Patterson used zircon crystals. They form with trace uranium. They form with no lead at all. Any lead found inside them should only come from decay. The uranium measurements were consistent, predictable, reliable. The lead measurements were not. They were far too high, too inconsistent, and impossible to reconcile with the theory. At first, the explanation seemed simple. Contamination. A flaw in technique. A problem with the laboratory. But the results did not change. No matter how carefully the experiments were repeated, the lead remained. At the same time, outside the laboratory, a different kind of problem was being solved. Engines were becoming more powerful. Cities were filling with cars. Mechanical limits were being pushed. Engineers were not looking for lead. They were not measuring isotopes. They were trying to make machines work better. Both efforts were rational. Both were driven by progress. And neither appeared connected. Not yet. What Patterson was measuring was not an anomaly. It was a signal. The problem appeared mechanical. As engines became more powerful, a new issue emerged inside the cylinder. Fuel ignited too early. Pressure waves collided. Metal vibrated under stress. Engine knock. It reduced efficiency. It damaged components. It limited how far performance could be pushed. The solution was not redesigning engine. It was changing fuel. Different fuels resisted compression differently. Some detonated early. Others did not. Chemists quantified this behavior. They called it the octane rating. Higher numbers meant greater resistance to premature ignition. Higher numbers meant smoother operation. Engineers needed an additive. Not expensive, not scarce. Effective in small amounts. After years of testing compounds that failed, one worked. Tetraethyl lead. A fraction of a gram per gallon was enough. The knock disappeared. Engines ran smoothly. Performance increased. From a technical perspective, the decision made sense. The additive was cheap. It was effective. It required no changes to existing infrastructure. Production could scale immediately. The fuel worked. The engines worked. The system advanced. At that moment, the problem seemed solved. No one measured where the lead went next. The engines did not fail. They ran better. Cars accelerated faster. Fuel burned more efficiently. Mechanical limits were pushed back. With every mile driven, the additive did its job. And then it left the engine. The lead did not disappear. It did not stay contained. It exited through exhaust pipes as fine particles. Into city air, onto roads, into soil and water. Millions of vehicles repeated the process every day. The distribution was uniform, uncontrolled, invisible. Lead settled on buildings, on crops, On playgrounds, it entered lungs with each breath. It entered bloodstreams. It accumulated slowly. There was no threshold event, no single moment of failure. Exposure was incremental, measured in years, measured in childhood. By the time symptoms appeared, they did not point back to engine. They appeared as learning difficulties, as behavioral changes, as unexplained increases in cardiovascular disease. In laboratories, the measurements continued to fail. Lead appeared where it should not exist, in rocks, in samples meant to be pristine. What had been released into the air was now embedded in the environment. The system was working exactly as designed. The consequences were working too. The problem did not resolve itself. In 1952, Claire Patterson moved to Caltech. He built a new laboratory from scratch. Walls were stripped. Electrical cables were removed. Lead solder was eliminated wherever possible. Floors were cleaned daily. Air was forced outward, never inward. Anyone entering wore protective clothing. The room was designed to keep lead out. Inside it, Patterson changed his approach. Earth's oldest rocks had been recycled by tectonic. Meteorites had not. They formed at the same time as the planet. They drifted untouched for billions of years. If lead was present there, it had meaning. Patterson measured 5 meteorites. Using 3 independent dating methods, the results converged. 4.55 billion years. The age of the Earth was no longer the question. The contamination was. Patterson began measuring lead in places far from industry. In the open ocean. At different depths. If lead were natural, its concentration would be uniform. It was not. Levels near the surface were nearly 10 times higher. The signal pointed upward, toward recent history. To trace it further back, Patterson turned to ice. Greenland, Antarctica. Each layer recorded the atmosphere of its time. The pattern was clear. Lead levels rose and fell with human activity. Mining, smelting, empire, and then, in the 20th century, they spiked. The data did not accuse, it did not speculate. It described a timeline, and the timeline matched the age of leaded gasoline. The measurements moved from environments to people. Patterson examined lead stored in the body. Bones, teeth. For comparison, he analyzed remains from long before industrial fuel. Ancient populations. Minimal exposure. The difference was not subtle. Modern bones contained hundreds to thousands of times more lead. In children, the effects appeared early. Lead mimicked calcium. The body absorbed it, stored it. The brain was the most sensitive target. Even low exposure interfered with neural development. Learning slowed. Attention declined. Behavior shifted. There was no safe threshold. Blood lead levels, once considered acceptable, were revised downward. Again and again. The changes extended beyond classroom. Across multiple countries, a pattern emerged. Rising lead exposure in early childhood, followed decades later by higher rates of violent crime. The timelines aligned, not perfectly, but consistently. Lead was not the only factor, but it was a measurable one. The cost accumulated quietly in lost cognitive potential, in increased cardiovascular disease, in premature deaths. Estimates varied, but the scale did not. Millions of lives shortened, hundreds of millions affected, all from a solution that had worked exactly as intended. The response came slowly. Warnings had existed for decades, so had resistance? Lead was profitable, embedded in infrastructure, defended as necessary, but the data accumulated. Countries began to act. Leaded gasoline was restricted, then banned. The effects followed with delay. Blood lead levels declined. Children born later carried less of the burden. Public health improved in measurable ways. Globally, the removal of lead from fuel saved millions of lives and trillions in economic cost. But the problem did not vanish. Lead remained in soil, in water systems, in industrial processes. Aviation fuel still used it. Batteries continued to spread it. The legacy was incomplete. Thomas Midgley did not live to see the full consequences. After contracting polio, he built a system of ropes and pulleys to help him move. In 1944, he became entangled in the device. He died by strangulation. The inventions he left behind outlived him. They reshaped the environment, they reshaped human health, and they forced a question that did not end with him. The decisions were rational. The data came later. The damage lasted longer than anyone expected. No single moment marked the turning point, only a sequence of improvements that worked. This is how progress often looks in real time: useful, efficient, incomplete. The question is not whether this could happen again. The question is whether it already is. When a solution solves today's problem, but defers tomorrow's cost, who is responsible for what comes next?